uh, record this just so I can share it out. Um, and yeah, we'll get going. Thanks so much, you all, for being here tonight. Like after a day of work or just life. I know it's really hard to do one more thing, especially a number of you are on the East Coast like myself. So 6 o'clock East Coast time on a Wednesday, diving into a webinar, maybe not the top of the list, but I appreciate you being here tonight and giving me a chance. The plan for this evening is to engage with the data puzzle instructional framework in the context of this lesson here. Not all warming is equal, and it's a resource that I'm really excited and proud about, actually. This is a data set that was embedded in a unit I had previously written um, about Arctic amplification, why the Arctic, as you can see in this graphic here, is warming faster than the rest of the world. And I was excited about this. Maybe it's a tough graph to look at, maybe because of what it means and what it's saying, but excited to pull it out of that unit and repackage it into a different product because I think it's such an important data set to look at. And so this is one of two different data sets we'll talk about tonight that are embedded in this Not All Warming is Equal data puzzle lesson, and it's meant to be a data set where we can start the conversation about the inequities of climate change. For those of you that may not be familiar, data puzzles are three-ish day long lessons that combine classroom-friendly data sets that are curated by scientists that we work with with the research-backed instructional practices of ambitious science teaching to support students making sense of phenomena. So in this case, we're looking at one of the data sets here. We'll talk about the ambitious science teaching practices embedded in data puzzles. And the phenomena we're exploring is the inequity of climate change. Um, Yeah, and again, forgive me if you've heard this, but just to introduce myself, my name is John Griffith. Who am I? I am an anxious father of a 3-year-old who's running around over my head right now, and I've got a little boy on the way, perhaps as early as this weekend. So it's a little bit chaotic here. In my past life, I was a climate scientist turned eighth grade science teacher and then chased my now wife to Denver, Colorado back in 2019, where I was hired to work with scientists at CERES, the Cooperative Institute for Research in Environmental Science, to bring their research into classrooms by developing what I hope are innovative resources. So I'm part of this CERES team, this education outreach. We're now the education engagement and evaluation team, and I'm the talking head tonight for a hugely collaborative team. Dr. Anna Gold, my supervisor, and collaborators Elise and Amy here. Just huge in the development of each of these lessons, these resources. And then a number of colleagues, just to name a few, Dr. Melissa Bratton, who's a co-author of Ambitious Science Teaching, was a mentor and a colleague in the development of this instructional framework. That was great. This was a textbook of mine when I was going through a teaching certificate program, and so it's been really exciting to get to work with the author of that textbook and learn from her directly. And then it's been exciting to get to work with scientists like Dr. Jen Kay and others. Jen is featured in this data puzzle lesson because she curated the data set that we're going to be talking about. And I should put a plug in here. Jen is going to be joining for a classroom call October 28th, and I'll talk a little bit more about that at the end. So what I'm kind of trying to do is introduce a data puzzle lesson early in the month, and then have the featured scientists in that data puzzle be available to speak to classrooms at the end of the month. So perhaps teachers would have a few weeks to implement that resource and kind of lay the foundation and give some context for a presentation where they would be able to ask that scientist question. So Jen is the featured scientist in the resource we'll talk about tonight, and she is going to be available and facilitate a classroom call later in the month. And so you'll see, I'll kind of start. I was hired in 2019, and I'll kind of guide you through the story of how we got here, and this will probably help you understand why there are so many Arctic data puzzle lessons. But in 2019, I was hired to connect the public, largely middle and high school classrooms, to this historic Arctic expedition where these scientists were studying all parts of the Arctic climate system for an entire year to better inform climate models for that region. There's more uncertainty in climate models for the Arctic than anywhere else on Earth. And so by gathering observations, measurements on the ground, we can better create these models, make them more accurate, more robust for the Arctic and then the rest of the world. And in developing resources related to the Arctic, like I'd mentioned earlier, I found that I was having access to some really compelling data sets that I would have really liked to have access to when I was in an eighth grade classroom. But many times they were buried in these large units. So I was concerned that maybe teachers weren't getting to that point because there's just so much. So um, worked with our friends at Data Nuggets to take a data set and put it into their framework and get that out through a data nugget. But wanted our own kind of flexibility in how we could develop resources using classroom friendly data sets and my background as an educator and in my education was all about ambitious science teaching practices. And when I used these practices in my eighth grade classroom, I found it more like a little easier to connect with the next generation science standards. Ambitious science teaching is all about using student resources, gathering evidence, constructing, revising models to explain phenomena. And so wanted to use these classroom-friendly data sets and use instructional practices that I was comfortable with and that were research backed to create my own product. And so out of that came data puzzles. And for those of you that may not be familiar with these ambitious science teaching practices, this is a pedagogical framework with tools, principles to support meaningful, equitable planning for science education. And there are four practices that they call out in that ambitious science teaching textbook, listed here in these quadrants and again, these bullet points. And the framework is all about supporting teachers and planning and designing lessons and units for instructions for their instruction. And so what I was trying to do is figure out a way to take these bullet points and create my own resource. Like how could I embed these practices into a scaffolded product so that teachers didn't have to do as much of that heavy lifting. It's a lot of work to create curricula, as you all know, and you're so busy with your students. Like I wanted to be that person that created something that was ready to go. And so we've taken this instructional framework with the support of Melissa Bratton and the other authors of Ambitious Science Teaching and created our own kind of instructional framework that utilizes those ambitious science teaching practices. You'll see that some of these, at least these two quadrants, are shifted relative to the ambitious science teaching instructional framework, and that's because this first quadrant here in the upper right corner is planning for engagement with important science ideas, and I've tried to do that planning for you, so you're not planning to engage with these important science ideas. I've done that for you, and instead you're already at the supporting students in identifying the important science ideas. So These have been swapped, and in each data puzzle lesson, we start by eliciting students' ideas. So, what do students already know? What experiences? What language do they have that could be used as resources later on in your instruction? And so, in each data puzzle lesson, there's an opening scenario. The scenario is kind of like about an everyday thing that students could connect with. And we want to hear what students have to say about that opening scenario. The opening scenario has similarities to the science investigation that will be presented later in the data puzzle. But the idea here is like before we say, why is the Arctic warming faster than the rest of the world? Maybe we talk about like snow in their backyard, or why does the snow melt faster on pavement than grass? So something that they may have experienced before we start talking about it in a context that maybe they're less familiar with. So after we've revealed student resources about an opening scenario, we dive into the featured scientists' research, and we try to connect student resources elicited during that opening scenario to the featured scientists' investigation. And this is done through an interactive reading we call a puzzle plot. Students summarize important science ideas in the puzzle plot through an initial model, and then they make predictions about an investigative question, a question that that featured scientist is investigating. Then students test their prediction against a classroom-friendly data set. So they're analyzing that data set, trying to identify patterns, and then revising their prediction based on evidence. So what did they think initially? And after exploring the data set, now what do they think? And then we put it all together, put the pieces of the puzzle together, so to speak, to construct a final evidence-based explanation where we reflect on all the evidence that we've gathered through these other practices to revise our initial model for that phenomena, for that investigative question. There's always a digging deeper question at the end, trying to take what students explored in the resource and challenge them to maybe think about it in a different context or think about social justice issues or climate justice issues that are connected to that phenomena. So uh, you can think of these as the practices kind of anchoring the lesson, and then these bullet points in the chalkboard being maybe the steps or the tasks that happen within each quadrant. I forgot to look at the chat. Oh, great. So given that context, like I wanted to dive into this not all warming is equal lesson so we can explore each of those ambitious science teaching practices and what they look like in an individual lesson here. Before we dive into the lesson together, what I wanted to do is just first pause and show you all of the resources that are available to you should you choose to use this data puzzle lesson or any of the other 15 that we have here. So this is the data puzzle site. I should have done this earlier, but I'll add it now. Sometimes I just can't believe I still forget to do this stuff, having done it so many times. But what I just added to the chat, for those of you that have access to a computer, is the landing page for tonight's webinar. And so this has all of the resources that I am referencing in this hour-long session. So totally understand that there's going to be too much here to probably take in, and so wanting to put all of these resources in one place for you so you can go back and find these things. So the data puzzle website, the slide deck we're using tonight, as well as all of the resources for this particular lesson and upcoming professional learning offerings. So where I am, I'm clicking on this data puzzles page, takes me to this home page, and then I'm going to go to the collection here. And these are the data puzzle lessons that are available. I'll also point out, like that was a pretty brief summary of the instructional framework. If you wanted more, there's a framework tab here with the graphic we just discussed. And then there are like practice documents that talk about the goals of each of these parts and describe the different steps in more detail. And there are some examples of what that look like, what they look like in the context of individual lessons. We also have some classroom footage here if you wanted to see what those practices look like in a seventh grade classroom in Boulder, Colorado. The collection, not all warming is equal. We'll dive into that. All of these pages look the same. There's some kind of context, background for use. And if you scroll down, the teaching materials are here. We know from doing some analytics and heat maps that the most popular way to access our resources are through this Google Drive page, this Google Drive folder, I should say, because you could see everything here. So if you click on these pages, you can see there's an answer key, a slide deck, a student worksheet, and a teacher guide for each data puzzle lesson. Teacher guides all look the same. A little bit of context, setting the stage. The four parts of a data puzzle lesson are the four parts of ambitious science teaching and how they show up in the lessons. And these different parts are described in more detail below. Page two um, of the teacher guide, they all look the same. It's an instructional overview with connections to the next generation science standards, driving questions, materials, new vocab, and then you'll see down below the different parts are described in more detail. Um, this one is a little bit long, looks like 6 pages. Oh, because there's some additional resources at the end, but no teacher guide is longer than 6 pages. They should be hopefully four. This one's a little bit long, but I know that, from my own experience, I'm not going to read a 20-page teacher guide. So I don't want to produce 20-page teacher guides. I'm trying to keep everything tight, so that it's as user-friendly as possible. If we look at a student worksheet, these all look the same too. So this is the student worksheet for this resource. I'd mentioned this earlier. There's a puzzle plot, so some background text to introduce the featured scientists and introduce some of those important science ideas. So there are some graphics that our graphic designer Amy Niku-Schmidt made specific for this resource. Some built-in questions. There are some videos too that are embedded in these puzzle plot texts. So uh, well, I'll mention this in a moment, but a lot of times these are read and engaged with collaboratively as a whole class, so that there are these pause moments to summarize, answer a question, or talk about an image or watch a video. Page two is where students summarize some of the important science ideas from that puzzle plot text. And so in this case, they're looking at a graphic and describing what they see and differences between the two graphics. There's space for students to jot down a question that the featured scientist is investigating. And in the text, it says, the question the science Dr. Jen K is investigating is dot 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 dot. So it's very explicit in the text what the question is, and then students make a prediction about that question. Then there are some data sets with scaffolded questions and an opportunity for students to revise their prediction based on new evidence. And then students construct a model to represent their new understandings as it relates to a question, and then some closing questions. So you can see there's a lot here, and the goal is that you're working through this with students. There's a slide deck that goes along with it. It's not, um, for lack of a better word, I would call it in my classroom, this isn't meant to be a shut up in color, like just pass it out and then forget it. It's meant to be like a very collaborative experience where students are learning with and from one another. Any questions about the student worksheet, teacher guide? You can see there's an answer key in there as well. Great. Then we're gonna dive into the lesson slide deck and explore it together just so you get a sense of what the progression is like, how you go from one practice to the next. The slides that we're going to look at here are from the slide deck for this lesson, but they're not comprehensive. So there are more slides in the slide deck than what you will see tonight. Just selected slides to convey certain points and to give you a taste of what's there. So just wanted you to know that yes, these are slides from the slide deck, but there are some more. So all data puzzles start with this eliciting students' ideas practice. The goal of this practice is to bring out student resources about an opening scenario, an image, a prompt, a video, a demonstration. And that opening scenario is going to have similarities to the science investigation presented in the data puzzle. So we're bringing out student resources that we can leverage and use to support students in making sense of a new phenomena. So for this, I will say, I always put this note here because I'll forget, this is not included in the student worksheet. This is this is done through a slide deck. There are discussions that you could have with your students. Students have done, or teachers have used a warm-up prompt as a way to engage their students with the opening scenario. Teachers have used whiteboards, think, pair, share, whole class discussions. So kind of up to you how you would facilitate this eliciting students' ideas practice, this opening scenario, but again, it's not in the slide deck. For this lesson, the opening scenario is asking students to think of a time when they were outside on a hot summer day. Maybe they were walking the dog or playing in their backyard or shooting some hoops. And it's a really hot day, 100 degrees. But is it 100 degrees everywhere? Are there some places outside that maybe are hotter than others? And so I want students to think about that hot summer day, and I want them to maybe hopefully get excited about sharing what they were doing, how hot it felt. Like, where did they go? Did they go find some shade? Did they go to a pool? Did they get a treat? Like, how did they find some refuge in this heat? And just the point is to show that even though the temperature is 100 degrees, it's not necessarily 100 degrees everywhere. There are places where it's hotter or colder, and that the same can be said for global temperatures. Global temperatures are on the rise, but just like your neighborhood, some places on Earth are warming faster than others. In this, we're looking at a global temperature anomaly graphic. This is showing temperature anomalies, the temperatures in 2022 related to this 1951 to 1980 average. And you can see some places are warming faster than others, warmer than others in this year. So kind of the same-ish thing, right? Global temperatures are rising, but some are rising faster than others. And that's what Dr. Jen Kay kind of studies with her work. She's an atmospheric scientist at the University of Colorado Boulder, and she does all sorts of work with climate models to study factors contributing to the rise in global temperatures and why some areas are warming faster than others. And so she knows that temperatures are rising, and this is caused by human activities. But she's seeking to understand why some parts of the Earth are warming faster than others. So hopefully you can kind of see we're starting with a student experience and trying to connect that to Dr. Jen Kay's work. And at this point, it's like, well, let's go learn a little bit more about Dr. Jen Kay's work through this interactive text called a puzzle plot. So again, these three slides are not in the student worksheet. At this point, this is when I would distribute the student worksheet to students so that we can learn a little bit more about Jen's work. And that brings us to part two, identifying important science ideas, or the goal of this practice is to identify important science ideas introduced in this interactive text, the puzzle plot. So what you're trying to do here is support students in connecting science ideas from the reading back to that opening scenario. Students are asked to summarize important science ideas by creating a sketch, or in this case, looking at a sketch and describing differences. So just being able to either draw an annotated sketch, um, create an annotated sketch, or describe one. Just the ability to see that is helpful for students, and then students identify and make a prediction about an investigative question. Are the actual data sets available? Caroline, that's a great question. So the visuals that you'll see here are developed with from Jen's climate model work. So we don't have an actual like spreadsheet of numbers. This is all from her climate model work. So I do have some information about like how Jen curated the data set and why there are certain time periods selected, um, but not actual numbers or values where students could graph things on their own. In this particular part here, when you've distributed this puzzle plot text, most classrooms, I would say this or facilitate the reading of this text through a whole class read aloud. Perhaps if it's a high school classroom and students are ready to kind of read through this on their own and watch these videos on their own. I always encourage teachers, if you use close reading strategies in your classroom already, please continue to do so. They're typically great. And if you have that routine in your classroom, please feel empowered to continue using that with this resource. The only prompts tasks we suggest is asking students to circle the investigative question in the text and asking them to underline similarities that they might find between the reading and the opening scenario. All these data puzzles have discussion prompts after the reading of the puzzle plot text, where we try to get students making connections between their everyday life and what they just read about. So this is the puzzle plot text for the not all warming is equal data puzzle. You can see this first graphic here, we're trying to talk about Earth energy budget and introduce the greenhouse effects. Here we're talking about a rise in global atmospheric carbon dioxide concentrations, and this video makes the connection between carbon dioxide and calls the carbon dioxide the steroids of the climate system. And we can see in this graphic here, there's a relationship between blue, which is global temperature, and green, which is the concentration of atmospheric carbon dioxide. The rise in temperature being related to the rise in atmospheric carbon dioxide. And so asking students to like think about Earth's energy budget, think about what would happen if you had more CO2 in the atmosphere. Um, and back any claims up with evidence in the form of data here. After we've gone through that puzzle plot text, like I showed you in the student worksheet, we're asking students to describe why global temperatures have increased since the start of the Industrial Revolution by looking at those two graphics. Record the investigative question, which for this resource is, do the places on Earth where temperatures are increasing the most also have the greatest increases in atmospheric carbon dioxide? In other words, are the places that are emitting the most carbon dioxide the same places where we see temperatures rising the fastest? Um, we ask students to make a prediction about this question, and on the screen here is a shot of the answer key. So you can see asking students to describe why global temperatures have increased since the start of the Industrial Revolution. There's a before and after here. And the goal here being that after we see more of the heat the infrared energy, heat energy emitted by Earth that previously escaped through Earth's atmosphere is being absorbed and re-emitted by greenhouse gases, effectively trapping heat in Earth's atmosphere. So, wanting to really emphasize, get students to describe the greenhouse effect, the question, and then a prediction. And after this, students are prepped to test their prediction against a classroom-friendly data set. So an emphasis here is to have students talk about the graphs before asking them to interpret them, identify patterns. So there are prompts in the slide deck that force students to talk about the graphs before they work individually in pairs. We have a lot of teachers using this what I see, what it means strategy. So in addition to talking about it, maybe students, it's almost like a notice wonder kind of thing. Students jot down what they see, what they observe, and what they think it means directly on the graph. So perhaps a strategy that could be used in conjunction with talking about the graphs. So here's a little bit of background, Caroline, about how Dr. K gets her data. She's a climate modeler, and so she's using mathematical equations with what we know about Earth system processes to predict past, present, and future climate conditions. So there is a little bit more information about the climate models that she used to create the graphics that you'll see. But that's about it here. So we're going to look at some of the data collected by these climate models to look at how things have changed from the early 1900s to the present day. Here are the graphs that are, or the data visualizations that are in this particular data puzzle, and some of the prompts that we ask you to consider talking about with your students. So what do the different colors represent? And what color is the United States? What do you think that means? This particular data visualization is looking at the change in surface atmospheric carbon dioxide concentrations. And it's a change from this 1900 to 1914 average to the 2000 to 2014 average. So it's the change in atmospheric carbon dioxide concentration between this average and this average. So the darkest red is saying that atmospheric carbon dioxide concentrations were 123 parts per million greater in 2000 to 2014 than 1900 to 1914. Again, those time periods and this 100-year gap were selected based on the climate model that Dr. Jen K used. And so we can see the darker reds have a greater change in atmospheric carbon dioxide, a greater increase in the concentration in those areas. As we go down to these yellows, the change becomes a little bit less. Globally, no matter where you are, atmospheric carbon dioxide concentrations have increased, but they've increased more in some of these different areas. We talk about the US here. What do you think it means that it's this particular color? So wanting just to get students cued in on different areas, get them thinking about the legend here before we ask them to look at some patterns. And what you might see here is the Northern Hemisphere sees the greatest change, the greatest increase in atmospheric carbon dioxide. And we see some of these developed areas over parts of Asia, Europe, the United States have these darker colors, indicative of a greater change, a greater increase in surface atmospheric CO2. We can compare that to global temperature anomalies, the change in surface temperature over that same time period. So this figure shows the change in surface temperature from 1900 to 1914 to 2000 to 2014. So the average temperature in these two time periods, this is showing the difference in the average between those two time periods. And the northernmost latitudes, the Arctic, really jumps out at you. This is an area that's warmed by anywhere from 4 to 5 to 6 degrees Celsius over this 100-year time period. We've got parts of the Antarctic warming quite rapidly as well. Something in South America here, lots of orange, yellow, kind of 1, 2 degrees Celsius for much of the globe, but some really rapidly warming areas. And so um, in the lesson, we're asking students to think about the relationship, like what do they see here? Where do they see the greatest change in atmospheric CO2? And where do they see the greatest increase in temperature? Right? It really jumps out. We see that these areas that are really developed nations maybe are not the same areas that are warming most rapidly, right? And so there's our inequities of climate change link. So in the student worksheet, we're asking students to, once we've talked about these data sets, to look at them, to answer some scaffolded questions, again, getting them to think about the change in these in temperature, the change in atmospheric carbon dioxide, and where the changes are greatest and where the changes are the least or most diminished. And after students answer some of those scaffolded questions and revisit their prediction, it's on to the final part of these data puzzles where they're asked to finalize new understandings by constructing an explanatory model. Depending on how familiar your students are with constructing models, it could be wise to spend some time reviewing modeling conventions, how to use different signs and symbols, perhaps show a model, show an annotated sketch representing some phenomena, and have students talk about what they see. Just give them some context before you say, go build the model now. Students should never construct these in groups of three. I made this mistake too many times in my eighth grade classroom. There's always somebody not doing something. So groups of two was kind of my go-to, and data puzzles, a lot of times students construct them individually and then have a chance to look at one another's kind of through like a gallery walk or something. And in this case, students are asked to annotate this particular background image. So this is the same map, had our graphic designer construct this same map that these different colors, temperatures, and CO2 changes are mapped on. So they're going to annotate on that same graphic. There are prompts to ask students to think about, and you could, if you're working with high school students, maybe you wouldn't need these, maybe you would. Like how could you use these thermometers to show change in temperature? How could you use cars and smokestacks to show changes in atmospheric carbon dioxide? So just a level of scaffolding, thinking about using these symbols to showcase some of these different ideas to address this question. Do the places on Earth where temperatures are increasing the most also have the greatest increases in atmospheric carbon dioxide? Really trying to get students to cite evidence from the puzzle plot or perhaps more importantly, the graphs. They have data in the form of numbers to write the changes in temperature, the change in temperature, the change in CO2 in different places that perhaps they make note of with these graphics. So encouraging them to back up their claims with evidence. And here's maybe an example of what students could do. Uh, Thermometers in the Arctic filled to the top, the greatest increase in temperature over that 100-year time period. Thermometers in different locations showing kind of low temperature, meaning it's still temperature is still increased, but not by 4 to 6 degrees Celsius, 1 or 2. And then thinking about atmospheric carbon dioxide, changes in carbon dioxide concentrations, why might it be more, that change be greater in some of these developed nations? Maybe they'd have some smokestacks and cars in this area. So just an example of maybe what we might look for in a model here. The last couple questions are digging deeper questions. Again, I should have mentioned this. All of these resources are in our Google products. Google Slides, Google Docs. So we encourage you to make copies of these for your own Google Drive or your own space, and then edit and modify them to meet the needs of your students. So, a question that might come up for students is why is the Arctic warming faster than other places? And perhaps we start to get into that, thinking about how the decline in sea ice might lead to amplified warming in the Arctic. And so I'm trying to use this graphic to demonstrate what we know to be true, and that is that the rise in global temperatures initiated a decline in sea ice. Sea ice is highly reflective, so incoming solar energy that was previously reflected off the sea ice is now being absorbed by the ocean surface. So the surface that was previously covered by ice, and that's contributing to this amplification up there. Decline in sea ice, more energy absorbed by the ocean up there, further amplifying the warming. And then another question, getting at more of the inequity piece. There are only about 4 million people that call the Arctic home. They contribute a very small amount of CO2 to the atmosphere relative to those of us at lower latitudes. So it's safe to say that they're not contributing the same to warming temperatures as other folks. So do you think that countries that emit the most should have to pay for the damages up there? Or how do you think those of us at lower latitudes maybe should could be held responsible for that or make some changes? So, an interesting way to think about the inequities of climate change. The people emitting the lowest amount of CO2 experiencing the greatest impacts of that. Lots of different resources, readings, videos, things you could pull to talk about this, but just an interesting prompt, an interesting way to get students thinking and talking about that based on the work that they've done in the data puzzle before. So that is the data puzzle for not all warming is equal. Again, we'll look at the student worksheet. There's the puzzle plot text. There's identifying the important science ideas, so summarizing important ideas from that text, identifying a question, making a prediction about that question, talking about some of these data visualizations and having students after they've talked about it answer some questions. Um, and then have students revisit their initial prediction for that question based on maybe revising it based on new evidence. They construct a final model and then a couple of digging deeper questions. And like I said, all of this you can make copies of and modify however you see fit. My goal is for them to be as plug and play as possible, but we know that I know teachers, myself included, we like to do whatever we like to do. And so, use this however you wish, but should you choose to use it, it's useful in its current form and it's as easy on you as possible. I wanted to just briefly put a plug in for this talk happening later in the month. So this is Jen K, and she's featured prominently in this resource, and she's going to be available October 28th for a 30-minute call. So this call we just did one a few weeks ago. We'll facilitate this. It'll be on a YouTube platform where you can see us, and it's a live stream of us, and questions and comments can pour in through the YouTube chat. And so Jen will talk about her work studying Arctic amplification in the context of the inequities of climate change, and then she'll talk for the first 15 minutes about her work and then be available to answer student questions and questions from the public for the last 15 minutes. So, what I'm trying to do is connect classrooms ideally to the scientists that they're reading about in texts. And so that's an October 28th event. And then in November, when I'm out on paternity leave, my colleague Elise Thurber will lead folks through another webinar like this, where we're kind of guiding. These are teacher focused, guiding folks through data puzzle lessons. This will be the wind farms of the future. So, an emphasis here, thinking about wind. Why is it windy in some places and not other places? Not pictured here, and an emphasis in this lesson. How it's really windy along the eastern and western coastlines, and getting students to think about how offshore and wind might play a role in renewable energy for the future, and lots of opportunities to talk about the pros and cons of that. So that'll be November 13th, from 4 to 5 p.m. Mountain Time. And the featured scientists from this data puzzle will give a talk probably early December. So again, it'll be that same kind of thing, data puzzle lesson, and then a scientist talk a few weeks or up to a month later, trying to connect students to the people in those resources. Um, Yeah, that's it. Any questions about all of this? I know that was really a crash course. So again, I'll put that landing page back in. I'm recording this in case you didn't get enough of it this first time. Maybe you'd like to watch something again. Maybe you forget something. I'll plug the landing page back into the chat. Um, and be sure to email it out to all of you again in case you click out of it. But this has the slide deck I just spoke to, a link to the data puzzle website, all of the resources that are available to you in this Not All Warming is Equal lesson, and then links to the two upcoming webinar events. One really intended for classrooms and kind of lifelong learners, and then this next one here being intended for teachers interested in specific data puzzle lessons. So I'll email this out again. One last thing, I am really interested in offering a PD certificate for anybody that wants one. So I'm gonna add this to the chat right now. If you could just drop your name, an email, and the subject you teach into this Google form, I'll be sure to send you a PD certificate for an hour for being here this evening. I'd also be interested in any ideas you have to make those scientist presentations more engaging for classrooms or more appealing for classrooms to join. We're just starting this webinar like staggered series, and it's at the request of teachers that we're doing this, and just wanting to make sure we're doing a good job and meeting folks' needs. So if you have any thoughts for me, that'd be great. So we've got a landing page, a Google form, and that's it. If folks have questions, I'm happy to hang out and chat. But yeah, I really appreciate you being here tonight.